Welcome to the course on power quality. So, we will discuss today the example on series active filters. So, starting with numerical examples. From the first example, design a single phase series active filter for filtering the voltage harmonics in 220 volt 50 hertz AC mains, which consists of 15% third, 10% fifth and 5% seventh harmonics present due to the other loads and source impedance before it is connected to a critical linear load of 3 kVA at 220 volt 50 hertz at 0.8 lagging power factor. If the single phase voltage source converter is used as a series active filter, calculate a voltage and current rating of series active filter, kVA rating of voltage source series active filter and the interfacing inductance of series active filter. Consider the switching frequency of 10 kilohertz and DC bus voltage of 200 volt with the allowable voltage ripple of 5% and ripple current in the inductor is 10%. So, these are typical circuit, like we have a AC mains and we have a typically a injection by series active filter of a suitable voltage and we have a linear load. So, we have a typically a distorted source voltage, but the load voltage is clean voltage. It means we have injected the voltage in series, so that the load voltage is clean and so that the load current, source current and load current both are same, because it is a series connected circuit and the injected voltage shown here by series active filter. So, let us come to the numerical part of this problem. Given that the supply voltage of Vs 220 volt, frequency of supply 50 hertz and the third harmonics Vs 3 is 15%, Vs 5 is 10% and Vs 7 5%. A critical load of 3 kVA at 0.8 lagging power factor is used and the DC link voltage of the series active filter is 200 volt, switching frequency 10 kilohertz and the filter ripple current 10% with the DC link voltage deviation permitted during dynamics 5% like. So, the just to go the load current, that is from load kVA divided by the voltage, it comes 13.636 ampere and typically the filter current 10% of this. So, this comes around 1.364 because series active filter is connected in series with the load like in the line. So, the deviation in DC link voltage is 5%, which comes because it is at 5% of 200 volt, so it comes 10 volt and the VDC minimum, if we calculate because of this 10 volt deviation, it comes 190 volt and the third harmonics is 15%. So, it comes of 220 volt of typically of 33 volt and fifth harmonics 10%, it comes 220 of 10% of typically of 220 volt, it comes 22 volt and 7th harmonic 5%, which is 11 volt like. So, the voltage and current rating of the series active filter is the RMS value of the third harmonic, fifth harmonic and 7th harmonic, and if keeping the value it comes 41.158 volt and the series active filter current is the same as load current, that is already we calculated 13.636 ampere and the thus the kVA rating of the voltage source converter of series active filter is your VFIS and putting the value of Vs, Vf 41.158 multiplied the current that is 13.636, it comes the rating 561.234 and the interfacing inductance of this series active filter, we can calculate from this relation VDC by 4 F into delta IF. So, putting the value it comes 3.66 millihenry. So, coming to the next example number 2, a single phase voltage source inverter with a square wave AC output of a 220 volt RMS at 50 hertz is feeding a critical linear load of 5 kVA 220 volt 50 hertz at 0.8 lagging power factor and design a single phase series active filter for filtering the voltage harmonics in this system to eliminate the voltage harmonics and to regulate the voltage fundamental voltage at 220 volt RMS across the load. If single phase voltage source converter is used as a active power filter, calculate the voltage rating of active power filter, current rating of active power filter, kVA rating of the voltage source converter of active filter and design an interfacing inductance and consider the switching frequency of 10 kilohertz, DC bus voltage of 200 volt DC and with the allowable voltage ripple of 5% and ripple current of inductor is 5% like. So, this is the typical circuit that we have a from the battery we are having a square wave inverter. So, we have a square wave, but we want sinusoidal voltage across the load. So, we have to inject a suitable voltage in series with the with the series active filter in series with the line, so that the load voltage becomes sinusoidal. So, after making a model, you can just see the load voltage is sinusoidal, and of course, the source voltage is square wave, and since it is the load voltage is maintained sinusoidal across the load, that is why the load current is sinusoidal as well as the source current is also sinusoidal, and the difference of these what the series active filter have to inject is the difference between square wave and sine wave, and this is the voltage waveform which series active filter is injecting like on top. So, just coming to a numerical part of it, given that supply voltage of Vs 220 volt, RMS is square wave, frequency of supply 50 Hz, a critical load of 5 kV at 0.8 lagging power factor, and VDC 200 volt, and switching frequency of 10 kilohertz, and the ripple current of 5% with the ripple voltage of 5% like. So, load current we can calculate from 5 kVA load with the at 220 volt, so it comes 22.27 ampere, and the ripple current, which is because active filter current is the same as the this load current. So, 5% of this current is comes around 1.36 ampere, and 5% of the DC link voltage of 200 volt, it comes typically of 220, it should come typically of 10 volt, I mean like, and typically the the VDC minimum should come typically of then 10 volt, so it comes 190 volt, and the supply voltage 220 square wave. So, VPCC is 220 sine wave. So, the voltage rating of series filter is the RMS voltage of the difference 2. So, we can calculate the RMS voltage of series active filter 2 upon 2 pi 0 to pi, because it is symmetric about so we can take half 2 upon 2 pi, and 220 minus 220 into root 2 sine theta square d theta. So, it comes 98.23 volt. That is the RMS voltage we have to inject from series active filter, and the current rating of series filter is same as the your load current rating. So, the load is 5 kVA, that is 5000 VA divided by the load voltage 220 volt, so it comes 22.27 ampere, and the kVA rating of the your active power filter is your Vf into Is. So, it is a voltage 98.23 multiplied the 22.27. So, it comes 2187.542 VA like. The interfacing inductance of the active filter is your LF VDC upon 4Fs delta IF. So, putting the value of this, we get the inductance value 4.401 millihenry like. So, coming to the numerical example 3, a series active filter consisting of voltage source converter with AC series injector and DC bus capacitor is used in series with the single phase AC supply of 220 volt 50 Hz, feeding a diode rectifier used for charging a battery of 240 volt at 12 ampere average current to reduce the harmonics in AC mains current and to almost maintain unity power factor. So, calculate RMS voltage at the input of diode rectifier, line current, then the voltage rating of active filter, current rating of active filter, VA rating of active series active filter, and value of the DC link voltage of active filter, and the value of AC inductor of series active filter. Consider the switching frequency of 10 kilohertz and ripple in the DC link voltage and inductor current are 5%. So, is the typical circuit like we have it here, the non-linear load that we are charging the battery with the diode rectifier. So, certainly like you will have a highly non-linear current if you do not put a filter, but if you put a series active filter and force the current to become continuous as a sine wave current, then you will find the diode will conduct for entire 180 degree. 2 diode for plus 180 degree, other 2 diode will conduct for minus 180 degree. So, you will find the voltage at the point of common coupling will be a square voltage of the output voltage of E. So, that is you can clearly see the supply voltage is sine wave, but the voltage at the point of common coupling, because we are making now current harmonics 0 in this case, it is a voltage fed kind of load, which I have mentioned in my typically earlier discussion also. So, we have at the point of common coupling here the square wave at the input of diode rectifier, and then we are forcing the current to become sinusoidal. So, current in line as well as load will be sinusoidal, and the difference of these two we are injecting, that is the reason, that is the input voltage is square wave. So, this is the typical voltage. So, here we are using a series active filter to eliminate the current harmonics typically in the, you can call it in source current and as well as in the load current, and we are injecting the appropriate voltage. So, it is working, you can call it a series active filter is used for eliminating the current harmonics typically in voltage fed kind of load. So, this is a voltage fed kind of load here like also. So, coming to the numerical part of it with the solution. the supply voltage 220 volt 50 hertz and load of DC link voltage of 240 volt and the DC link current of 12 ampere with the switching frequency 10 kilohertz and 5 ampere ripple current and 5% typically your voltage across the DC link, like deviation during the dynamics. So, coming to typically the active power drawn by the load, which is given the DC voltage is given of the battery as multiplied the current. In the load it comes 2880 watt and the supply current will be like your this power divided by your 220 volt. So, it is your 13.091 ampere, and if we take typically the filter ripple current, because supply current and filter current are there. So, 5% of this current will be your 0.655 ampere and the DC link voltage typically variation is 5% of VDC of active power filter. So, supply RMS voltage at the input of diode rectifier, which is like a square wave, will be the same as the DC voltage at the output, like. So, that is a 240 volt, and now the supply line current at unity power factor will be power divided by 220. So, that is same as we calculate 13.091 ampere, and the voltage rating of the series active filter we can calculate it, because supply voltage is sine wave of 220 volt RMS and peak will be 220 root 2 and the diode rectifier input is the 240 volt, and we can take, because it is a half wave symmetry. So, we can take 2 upon 2 pi and taking a root of this. So, we get this voltage 104.53 volt, and the current rating of the series active filter we already calculated, that is the load current and source current, that is a 13.091 ampere, and the VA rating of the series active filter for this current harmonic elimination will be the injected voltage by series active filter multiplied the current, and putting the value of these two we get the rating of 1368.407 volt ampere. And the voltage of the DC link voltage, we can find out from root 2 Vf upon Ma. So, putting the value of this modulation factor 0.8, so it comes 184.78. So, we can round off to 200 volt, and the interfacing inductance from putting the value of DC link, it comes like a 7.639 millihenry. So, coming to the fourth example, a series active filter consisting of voltage source converter with the AC inductor, coupling transformer and its DC bus connected to the battery functioning as a load shown in figure is used in series with the single phase AC supply of 220 volt 50 hertz feeding diode rectifier used for charging a battery of 192 volt at 25 ampere average current to reduce the harmonics in AC mains current, and to maintain unity power factor, calculate the RMS voltage at the input of diode rectifier, line current, voltage rating of series active filter, current rating of series active filter, VA rating of series active filter, the value of AC inductor, interfacing AC inductor, the turns ratio of the coupling transformer, consider the switching frequency of 20 kilohertz and ripple current inductor is 5% like. So, this is typically again the voltage fight kind of non-linear load, but what we are having here, we have to use a coupling transformer to make isolation, because the DC link of both series active filter and the load is common. And again here, since it is a voltage fed load, so we are eliminating the current harmonics, we are forcing the current to charge this battery with the sinusoidal current, and because of this you will find the diode will work as a router. So, the square wave voltage will appear at the input like. So, you can see the supply voltage sine wave, and to make this source current and load current sine wave, we are forcing to charge this battery entire 180 degree. So, diode will conduct. So, you will find this will be a square voltage at the input of diode rectifier, which the difference of which we have to inject, the difference of this sine wave input and this square wave we have to inject, and that is the voltage injected by the series active filter here like also. So, by injecting this appropriate voltage, we will be able to force the diode to conduct for and we will be able to make the current flowing into the sine wave like. So, coming to the numerical part of the solution, given that the supply voltage of Vs equal to 220 volt RMS and frequency of the supply 50 hertz, load consists of diode rectifier having a current of DC current of 25 ampere and a battery voltage of 192 volt. So, the active power of the load is VDC IDC. So, putting the value it comes 4800 watt, and the 5% of the ripple you can current of the IS, that will be 5%, and the current is typically 21.818, it comes 1.01091 ampere. And from this power divided by 220 we will get that current, and that putting the value here we will get this current source current, and from that we get the ripple current. So, the sine wave supply current after the compensation results in a continuous conduction of diodes of the rectifier for 180 degree, and it results in a square wave AC voltage at PCC with the amplitude of DC bus voltage of 192 volt. Therefore, VPCC will be 190 volt RMS like, and the line current at unity power factor will be power 4800 divided by 220. So, this will be 21.81 ampere, and the voltage rating of the series active filter will be the difference of sine wave minus the your square wave of 190 volt peak, and taking a RMS of this for 2 upon 2 pi for a half wave symmetry 0 to pi, it comes 95.94 volt, and the current rating of series active filter we already calculated earlier. So, it comes IF equal to IS equal to 21.8181 ampere, and the kV rating of series active filter is your VF IS, that is putting the value of your VF and IF, so it comes 2093.3 VA like, and the interfacing inductance of series active filter with the DC VDC of, and then because DC link is common and taking a ripple current. So, it comes to like a 2.2 millihenry like, and the turns ratio of the coupling transformer, I mean we can calculate that because we have to inject, typically you can call it from this DC link voltage of 192 we can develop maximum 135.76, and this typically is equal to, you can call it, we have to inject into the supply the voltage equal to this. So, the turns ratio will come because we have to inject this voltage and we are getting maximum voltage from the inverter this. So, the turns ratio of the transformer will be 1.41505. So, coming to numerical example 5, a series active power filter consisting of voltage source converter with AC series inductor and coupling transformer and its DC bus connected to DC bus of the load is used to reduce the harmonics in AC mains current and to maintain almost a unity power factor in series supply of 220 volt 50 hertz, feeding a diode rectifier load with a capacitive filter of 2000 microfarad and a resistive load of 10 ohm in parallel, and DC link voltage of the load is decided to result in a minimum injected voltage of the APF. Calculate the RMS voltage at the input of diode rectifier, line current, voltage rating of series active filter, current rating of series active filter, VA rating of series active filter, DC bus voltage of series active filter, and turns ratio of the coupling transformer used in series active filter. So, this is a typical circuit. I mean we can just see here on the DC link of load is common to the series active filter, and we have a coupling transformer here. I mean like, and we are forcing with by injecting the voltage in series with the line. So, that current, I mean sinusoidal current is there at unity power factor with the supply, but we want to have a minimum current, minimum VA voltage rating of the series active filter, and accordingly the DC link voltage is decided. So, in this case we can just see it is a supply voltage, and this much is the typically the voltage we have to regulate at the typically at the load across, which is the DC link voltage of series active filter also, and then we have a current sinusoidal supply current as well as the load current, and the difference of this is the typically the injected voltage. So, we are injecting the minimum voltage in a manner that the DC link voltage as well as AC RMS voltage both are same. So, AC RMS voltage should be such that we inject the minimum voltage like on also. So, coming to the solution part, given that the supply voltage Vs equal to 220 volt RMS, frequency of supply 50 hertz, and the load consists of diode rectifier 10 ohm. If X volt is the DC link voltage of rectifier load, then the injected voltage of series active filter is as Vf equal to under root 2 upon 2 pi 0 to pi 220 into root 2, that is a sine wave of 220 volt into sin theta minus x square d theta. This is the injected voltage, and this voltage we want to minimize this. So, after integrating and taking a derivative with respect to x, it gives x equal to 2 root 2 upon pi into Vs. So, it comes 0.9 Vs, and that nothing but VDC equal to 198.07. So, what we are doing, we are typically minimizing this, and this minimum will take place that when we really integrate and take a derivative of this. So, this gives us the typically the value of, you can call it the x value. This is the x value we are getting from here like. So, now once we got the x value, we can find out typically, I mean the, you can call it the load current. So, we know the VDC and we know the now the load resistance. So, we can get the load current 19.807 ampere like, and the active power is now VDC IDC. So, we can get total active power is 3923 0.175 watt, and now the sine wave supply current after compensation results in a continuous conduction of diodes of the rectifier for the duration of 180 degree, and it results in a square wave AC voltage at PCC with the amplitude of DC link voltage of 198.07. So, therefore, PCC voltage will be of a square wave RMS voltage 198.07 volt, and the line current at unity power factor is P upon Vs. I mean that is your the active power which we calculated there used for charging divided by 220 volt. So, it comes 17.833 ampere RMS like, and voltage rating of series active filter which we already calculated by this relation. I mean we got this value of the input of rectifier, this is the supply voltage. So, difference of these two we have to inject. So, we can calculate RMS from this relation by half wave symmetry 2 upon 2 pi 0 to pi, it comes 95.752 volt like, and the current rating of series active filter we already calculated from power and load resistance. So, this comes like a 17.833 ampere, and kV rating of voltage source converter of series active filter VFIS, putting the value of this it comes 1707.545 volt ampere, and the DC link voltage of the load is certainly same which we got the X 198.07 for the minimum injected voltage in series with the line, and the turns ratio of the coupling transformer we can find out that from this voltage how much AC voltage we can generate. I mean that is VDC by root 2, that is the voltage we can typically generate, and on the supply side we have to inject only the VF. So, turns ratio from this we can calculate, that will be the this much the voltage we can generate from the inverter, and this is the voltage to be injected into the supply. So, the ratio of this comes 1.463. So, this is on the inverter side, this is on the injected voltage on the grid side like. So, this is the turns ratio. Coming to the sixth numerical example, a series active power filter consisting of voltage source converter with AC series inductor, coupling transformer, and it is a DC bus connected to the DC bus of the load shown in the figure is used to reduce the harmonics in AC mains current and to maintain almost unity power factor in series of the single phase AC supply of 220 volt 50 hertz, fitting a diode rectifier with a capacitive filter of 1000 megafarad and resistive load of 10. If DC bus voltage of load is to be maintained constant ripple free of 320 volt, then calculate the RMS voltage at the input of diode rectifier, line current, voltage rating of series active filter, current rating of series active filter, VA rating of series active filter, and turns ratio of coupling transformer. So, in this case what we have, we know already this is 320 volt, it is given, that is virtually across the load we have to maintain, because it might be fitting a, this load may be equivalent to like a variable frequency induction motor drive. I mean, so we have to maintain this typically. So, the job of series active filter is one at making this supply current sinusoidal, power factor unity, and to regulate with the help of this control this load voltage, which because it is a common series active filter voltage, and this voltage to maintain this voltage at 320 volt, and that is the task. So, series active filter is not only really eliminating the current harmonics, but is regulating the DC link voltage which is the load voltage also. So, that is another additional task is given to this series active filter or this system like on. So, we have a supply voltage sinusoidal, we want this voltage of typically of DC link of 320. So, there will be now we are forcing with the because sine wave current. So, diode have to conduct for 180 degree. So, the same voltage which is 320 volt here it will come to at the PCC in the square wave form. So, this is the 320 volt square wave, and of course, with proper control we are able to have supply current and load current which are connected in series as a sine wave at unity power factor, and now the injected voltage will be a difference of this. So, now since we want higher the voltage at the output, so certainly the series active filter rating have to increase, because it has to inject the additional voltage, fundamental voltage also typically, so that this voltage increase to 320 volt. Like coming to the typical solution of numerical part of it, given that supply voltage of Vs equal to 220 volt RMS and frequency of supply 50 hertz, the load consists of diode rectifier with the resistance of 10 ohm and DC link voltage of 320 volt. So, load current will be your typically of your voltage divided by resistance. So, it will be 320 by 10 32 ampere, and the active power is typically VDC IDC, that is 320 into 32 is come your 10,240 watt or 10.24 kilowatt, and the sine wave supply current after compensation results in a continuous conduction of diode of the rectifier for 180 degree, and it results in a square wave AC voltage at PCC with the amplitude of DC link voltage which is VPCC equal to 320 volt. Therefore, VPCC 320 volt RMS. So, line current at unity power factor will be from the power 10,240 watt divided by 220 volt of supply RMS, and it comes 46.545 ampere. And the voltage rating of series active filter now we can calculate from the difference of the square wave of 320 volt and the sine wave of 220 into root 2 peak by half wave symmetry 2 upon 2 pi and 0 to pi RMS voltage, it comes like 155.034 volt like. So, now the current rating of the series active filter typically is your same as the supply current and load current 46.545 ampere, and the kV rating of the series active filter will be VFIF. So, keeping the value of both, it comes 7215.98 VA like. And the turns ratio of the coupling transformer will be now that maximum AC voltage from voltage source converter of series active filter we can generate 220 by root 2. So, it comes 226.27, and on the supply side we have to inject the voltage which we have calculated by. So, we have to inject the typically voltage of 155.0, and we can generate from the inverter 226.27. So, from this we can calculate the turns ratio comes to be 1.4595 like. So, coming to the numerical example 7, a single phase 230 volt 50 hertz diode bridge rectifier with the DC bus capacitive filter feeding a DC of 340 volt and 10 ampere average current to a variable frequency 3 phase voltage source fed induction motor drive in air conditioner, and single phase series active filter consisting of voltage source converter with series inductor, coupling transformer, and DC bus capacitor is used in series with the rectifier inverter system to reduce the harmonics in AC mains current and to almost maintain a unity power factor and to regulate the DC bus voltage of rectifier to 340 volt. Calculate the A RMS voltage at the input of single phase diode bridge rectifier, B line current, C RMS current of a series active filter, RMS voltage across the series active filter, and the V rating of your series active filter. So, these are typical circuit like we have a here you can call it the diode rectifier feeding a capacitor, you can call it a nonlinear load of voltage fed. So, it is a capacitor and we want this voltage to be 320 volt and is feeding to variable frequency induction motor drive. So, whatever voltage there we are with the help of series active filter we are forcing typically the sine wave current, and so that the supply voltage and supply current they are in phase and sine wave, and you have a unity power factor. So, now in that case when we are forcing to have a sine wave current into the diode rectifier, you will find the typically this DC link voltage will reflect here at the PCC with the square wave. So, with that after making a model and making a complete simulation with the realistic data, actual data. So, we got the let us say this supply voltage, we got the voltage at the diode rectifier input or voltage at PCC, it comes like a square wave, and the supply current and typically the AC side load current both are sine wave and in phase with the supply voltage, and the difference of the two, this is voltage at the PCC voltage and the supply voltage we are injecting by the series active filter with the help of this transformer and inverter like. So, coming to the numerical part of it, given that the supply voltage of Vs equal to 230 volt and frequency of supply 50 hertz, the load consists of diode rectifier having a 10 ampere and DC link voltage of 340 volt. So, active power P will be VDC IDC. So, putting the value it comes 3400 watt, and the sine wave supply after the compensation results in a continuous conduction of diode of the rectifier, and it results in a square wave AC voltage at PCC with amplitude of DC link voltage of PCC 340 volt, and therefore, PCC RMS is 340 volt, and line current at the supply we can find out the power divided by the supply voltage that is 230 volt. So, we get typically 14.783 ampere, and the current rating of series active filter will be the same because they are connected in series. So, it comes IF equal to IS 14.783 ampere like. So, now the voltage rating of series active filter we can find out VF equal to VF RMS, that is about half wave symmetry. So, we can take only half wave, half square wave 2 upon 2 pi 0 to pi, and this is 230 volt RMS, we take the peak that is a sine wave minus 340 that is a square wave, and we take a square with the RMS of it, it comes 166.405 volt. And now coming to the kVA rating of series active filter, that is S equal to Vf into Is. So, it comes voltage rating was we calculated 166.405 into the current rating 14.783 VA. So, it comes 2459.96 VA like. Coming to the numerical problems, design a numerical problem 8, design a 3-phase series active filter for filtering the voltage harmonics of 450 volt 50 Hz AC means having 15% 5th harmonic, 10% 7th and 7% 11th and 5% 13th harmonic present due to the other loads and source impedance before it is connected to critical load of 30 kVA 415 load 50 Hz at 0.8 lagging power factor. If 3-phase VSC is used as a series active power filter, calculate the voltage and current rating of series active filter, kVA rating of series active filter, interfacing inductance and the turns ratio of the coupling transformer. Consider the switching frequency of 10 kHz, DC link voltage of 200 volt DC and allowing voltage ripple of 5% and ripple current of inductor of is 5%. This is the typically of series active filter. So, we have a linear load here, we have a series active filter which takes care of this voltage harmonic compensation. This is the supply voltage, we have a load voltage which is filter after the injection of the load current, supply current, load current because series it is same and these are the voltage injected by series filter. So, coming to the solution part, given that base equal to 415 by root 3 and 50 Hz and 5th harmonic 15%, 7th harmonic 10%, 11th harmonic 7%, 13 5%, a critical load of 30 kV at 0.8 lagging power factor and DC link voltage 200, we can see 10 kHz and your ripple current 5% and DC link voltage ripple 5%. The load current is calculated from kVA, so it comes 41.736 ampere and the ripple current of 5% of is 2.087 ampere. Ripple voltage of DC link voltage of typically given of 200 volt, so 5% 210 volt and the minimum DC link voltage comes 191 and 5th harmonic 15% is 35.9 volt, 7th harmonic 10% 29.96, 11th harmonic 7% is 16.77 and 13th is 5%, so it comes 11.98 volt. So, the voltage and current rating of series active filter, all the voltage RMS value will be 14.86 volt and the filter current is the same as your load current is 41.736 ampere. So, kV rating of series active filter will be 3 into Vs into Is. So, putting the value it comes 5.992 kVA and the interfacing inductance of this from this relation from turns ratio and the ripple current. So, we get the LF equal to 1.498 millihenry and the turns ratio of the coupling transformer is computed on the maximum AC voltage of AC typically driven from transformer from the inverter. This is 56.97 and the supply must inject Vf. So, turns ratio comes from this generated voltage divided by the injected voltage, so it comes 1.18. So, coming to the 9th numerical problem, a 3-phase series active power filter consisting of voltage source converter with AC series inductor, coupling transformer and DC bus capacitor shown in figure is used to as a series in series with the 3-phase supply of 415 volt 50 Hz feeding a 3-phase diode rectifier load for charging a battery of 540 volt at 50 ampere average current to reduce the harmonic currents in AC mains current and almost maintain unity power factor. Calculate a RMS line voltage at the input of diode rectifier, which will be almost quasi square because we will be forcing all 3-phase current to be sinusoidal AC line current, RMS current of the series active filter, RMS voltage across the active filter, V rating of series active filter, AC inductor value, turns ratio of series active filter, coupling transformer used in series active filter. If the DC link voltage of APF is 400 volt, consider the switching frequency of 20 kHz and ripple in the DC link voltage. Deviation DC link voltage is 8% of its reference value or nominal value and ripple current in the inductor is 2%. So, these are typical circuit. We have a non-linear load of voltage fed kind and when we have a voltage fed kind of load, by injecting a suitable voltage we can force these current to all 3 currents to have a sinusoidal in phase with the supply voltage and that what it will cause, it means the diode will be conducting for 180 degree and with the 180 degree conduction it will be like a behavior that you have a inverter with 180 degree. So, the voltage here you will find kind of a your stepped voltage waveform what you get from 180 degree conduction of 3-phase inverter. So, by suitable injecting the voltage. So, PCC voltage will be of that kind of step wave. So, supply voltage is let us say sine wave 3-phase balance supply voltage. If we inject this kind of phase voltage, we will be able to force the continuous current of supply current which is sine wave and same will be the load current on PCC and the difference of these two voltage we have to inject. So, if we inject this voltage then this current will be automatically forced to become balance sinusoidal and the current can be maintained in phase with the supply voltage. So, this series active filter virtually here working for eliminating the current harmonics of this voltage fed kind of load. However, we call it series active filters should really work eliminate the voltage harmonic, but here we are injecting the current harmonic by let us say injecting the appropriate voltage in this series with the line. So, it comes like with the solution part, given that supply voltage V s equal to 415 by root 3 to 39.6 volt and frequency of supply 50 hertz, and the DC load voltage is 540 volt and DC current load current is 50 ampere, switching frequency 20 kilohertz, ripple current 2% and the deviation in DC link voltage is 8%, and we have a capacitor DC link capacitor voltage of active filter 400 volt. So, the active power from the load side we can calculate, which is given 540 volt 50 ampere. So, it comes to 27,000 watt or 27 kilowatt, and the supply current from this we can find out from this active power divided by, because power factor is unity, so 3 into phase voltage, that is 239.6. So, current comes 37.563 ampere, and now the filter ripple current is 2% of it. So, it is a 0.75125 ampere, and the DC link voltage deviation during dynamics permitted 8%. So, it comes like a 32 volt, and now the DC link voltage, which is a nominal DC link voltage 400 volt at the series active filter DC link. So, now it minimum will be 368 volt, from which we have to find out the turns ratio. So, the sine wave supply current after the compensation results in a continuous conduction of diode of 3-phase diode rectifier, each diode conducting for 180 degree, and it results in the waveform of the 3-phase of the phase voltage at the input diode rectifier at VPCC is a step waveform of a segment, first step of 60 degree pi by 3 angle from 0 to pi by 3, and the magnitude of VDC load by 3, and second step of pi by 3 angle from pi by 3 to 2 pi by 3 and magnitude will be 2 VDC by 3, and the third step of pi by 3 angle 60 degree again from 2 pi by 3 to pi and magnitude of VDC by 3, and it has a for both half cycle symmetric segments of such a step. So, RMS line voltage at the input of diode rectifier or PCC is computed as the sine wave supply current after compensation results in a continuous conduction of diode and result in a quasi square wave, and the DC, with the DC link voltage. So, PCC RMS voltage is your VDC upon root 2 by 3. So, it becomes 440.91 volt, therefore, PCC will be 440.91 volt, and the supply current we have calculated from power divided by the supply side voltage into 3 phase voltage. So, it comes 35.563 ampere, and the current rating of series active filter will be the same as the supply current, that is 37.563, since series active voltage connected in series with the supply, and the RMS voltage rating of series active filter VF is computed by taking a difference of supply phase voltage and the phase voltage at the input of diode rectifier edge. So, we have a in a half wave symmetry we have a you can call it like a typically of 3 segments of 60 degree. You can take half wave symmetry from 2 upon 2 pi. So, starting from 0 to pi by 3 we have a AC phase voltage 239.6 into root 2, that is a sine wave, minus the 180 degree, that we talk about VDC by 3. So, 540 by 3, that is first segment of 60 degree. The second segment of pi by 3 to 2 by 3 again is the 360 degree, that is 2 VDC by 3, and third segment is typically again VDC you can call it by 3. So, 540 by 3 180 degree. So, taking our all calculation it comes 75.6415 volt like, and the kV rating of VSC of series active filter will be 3 into VF into IS. So, it will be 3 into 75.6415 into 37.563 ampere, it will be your 8524 VA, that is the kV rating of the series active filter, and the interfacing inductance of series active filter will be your LF, the turns ratio, and then the ripple current relation from here. So, if you put all value, this your interfacing inductance comes 3.83 millihenry. So, turns ratio of the coupling transformer is calculated that what the inverter can generate the AC voltage. So, from modulation index of 0.8 and 400 DC link voltage. So, this can generate 113.137 volt, and on the typically on supply side we are injecting the VF voltage. So, turns ratio we can find out from this is the voltage what we are generating from the inverter, this is the voltage what we have to inject. So, from this we get the turns ratio of 1.4957. So, coming to the 10th numerical problem, a 3-phase 415 volt 50 hertz 6 pulse diode bridge rectifier with the DC capacitor filter feeding a 600 volt at 150 ampere average current to variable frequency voltage source inverter fed induction motor drive, a 3-phase series active filter consisting of voltage source converter with AC series inductor, coupling transformer and DC capacitor is used in series with the rectifier inverter system to reduce the harmonics in AC mains current, almost to maintain unity power factor and to regulate the DC bus voltage of the rectifier to 600 volt. To calculate the RMS line voltage at the input of diode rectifier, B line current, C the RMS current of series active filter, D the RMS voltage across the active filter and E the V rating of series active filter. So, these are typical circuit. Here also what we have a diode rectifier. We normally use the to reduce the cost gadget to derive the voltage source, DC voltage source, we use the diode rectifier and which is with the capacitive filter and which is feeding the variable frequency, or you can call it voltage source inverter fed induction motor drive, I mean 4. And now the purpose of this series active filter is that we inject the voltage to reduce the, it will draw very large harmonic current which we have seen earlier. So, by injecting suitable voltage we are able to maintain this supply current sinusoidal in phase with the voltage. So, virtually we are using a series active filter, you can call it for the purpose of in voltage fed kind of load, virtually reducing the current harmonics, like which could have been otherwise very high. I mean the TAD of the current otherwise is, if we do not use around 60 to 70%, we are able to reduce even less than 5%. So, after making the complete model with realistic data, we are able to get the result here. This is the supply voltage. We are getting, we are forcing by injecting a suitable voltage in series with, I mean this. So, I mean this DC link voltage will reflect here, because diode will conduct 180 degree. So, this kind of voltage, phase voltage will be reflected at the point of common coupling. And if we, I mean inject the difference of these two, which is the voltage here of series active filter, will be able to force this current sinusoidal and in phase with the supply voltage. So, it means on supply we will get a sinusoidal and current will be also, you can call it current will be sinusoidal balance at unity power factor, and this is of course the PCC current, because it is in series. So, both current will be the same. So, this series active filter virtually working for eliminating the current harmonics, typically not eliminating the voltage harmonic, but we are injecting the voltage and that is the in series. So, that is why we call it the series active power filter like. So, coming to the solution part, given that supply voltage of 415 by root 3, that comes to 39.6 volt and frequency of supply 50 hertz and DC load of 600 volt and DC load current is 150 ampere, I mean maybe large rating, you can call it like variable frequency drive. So, active power of the load will be VDC and that keeping the value of VDC 600 volt and IDC of 150 ampere. It comes typically you can call it 90,000 watt, means 90 kilowatt drive, and supply current will be from active power divided by the supply side per phase voltage multiplied the 3 for 3 phase. So, it comes putting the value 125.21 ampere on the supply side, balance current, sinusoidal current at unity power factor current like. So, now coming to the calculating the rating of the series active filter. So, sine wave supply current after compensation results in a continuous conduction of diode of the 3-phase diode rectifier, E diode conducting for 180 degree, and it results in the waveform of phase voltage at the input of diode is a stepped waveform, and the first step of pi by 3 angle from 0 to pi by 3 and the magnitude of VDC by 3, and second step of pi by again 60 degree from pi by 3 to 2 by 3 and the magnitude 2 VDC by 3, and the third step of pi by 3 angle, I mean that is 2 by 3 to pi and magnitude of typically VDC by 3, and it has a both half cycles of symmetric segment of such steps. So, the RMS line voltage at the input of diode rectifier is computed as follows. The sine wave current after compensation results in a continuous conduction of diodes of direct rectifier of 180 degree, and it results in a curve wave of AC voltage at PCC with the amplitude of DC link voltage of typically VDC by 2 root 3. So, it comes 489.89 volt. So, VPCC is also 489.89 volt. So, the supply current at unity power factor we calculated 90 kilowatt is the load multiplied 3 phase and unity power factor and the voltage 239.6. So, it is 125.21 ampere, and the current rating of series active filter will be the same because it is connected in series. So, filter current rating equal to supply current, it will be 125.21 ampere since APF is connected in series with the supply, and the RMS voltage rating of series active filter VF is computed by taking the difference of the supply phase voltage and the phase voltage of the input of diode rectifier as follows. So, this is typically 3 segments what we say, I mean 2 by 2, 3, 4, typically only 180 degree we are having. So, 0 to pi by 3, that is the phase voltage, sine wave 239.6, that is RMS voltage multiplied to peak voltage into sin theta minus the VDC by 3. So, we have a 600 volt VDC divided by 3, 200 square, and taking another segment pi by 2, 2 pi by 3 of this again sine wave minus the VDC 2 VDC by 3, that is 2 into 600 by 3, that is come 400, okay, and the third segment 2 pi by 3 pi. So, half cycle we are taking again 239 pi into peak voltage sin theta into VDC by 3 square. So, taking RMS of this, it comes only 89.323 volt, and the kV rating of voltage source converter of the series active filter will be your 3 into Vf into Is. So, it will be 3 into 89.323 into 125.21 Va. So, it comes 33.552 kVA. Like, can we stop here? Okay.